how to sum. So let us wait for half the class, and meanwhile you can think on this question, and I would like to answer that once the quorum is there. Right. So in all the different in all the classes, in various different ways, essentially what were we given? We were given some chemical process. We were given some chemical process, and some information about that process was also provided to us, right? And then we were asked to determine something, find this flow rate, or to determine something about that process, right? Essentially all the questions, the simple ones that we have done till now, were of this class. Am I right? Is it? I don't know. Am I audible?
Yes, sir. Can you just repeat it once?
Oh, yeah. So actually there's quite a lot of noise here. So construction work going on everywhere on campus. Maybe let me shut this window. Maybe. Right. Essentially, whatever we have done so far gave us some description of a chemical process, and there was some information provided to us about that process, and then we were asked to determine some quantity or some information, new information about that process, right? And generally we had a text statement which gave us the input, information in going in, and we were asked to find something about that process, right? So what we said is, how do we condense all that information? I mean, how do we summarize it? Or rather, the word I'm looking for is organize. How do we organize whatever is in words? How do we organize that information? Was our basic question. And we said that the appropriate form of organization is a flow chart, a diagram. So what did this flow chart contain? This flow chart had various boxes which represented the various units, we so far had a single process unit, but we will extend it starting say Thursday. So we had some reactor, or we had a mixer, or we had some distillation column. There was some process unit which we represented by a black box. And then we had
So you've been muted.
Sorry, I don't know. I didn't mute myself. Right. So to repeat, so we represented, we drew I asked you all to draw a flow chart based on the text of the statement of the problem. And so in that flow chart, what were the components? Well, the rectangle that you had was a box was representing some chemical unit, process unit, a piece of equipment, a mixer, a distillation unit, reactor, what have you, right? And then we also had arrows. These arrows could be inputs or outputs, and that's what they stood for. And such arrows you wrote for each process stream, and then you tried to include for each process stream all the information right on top of this flow chart. In other words, you try to label that chart. Essentially, this is what we have been doing. So it's like a cricket card. I mean, you at every time you have a chart or a score sheet, and you keep updating it. All right, now I found out this information, and this flow rate is now no more known. In the previous example, it was the flow rate of liquid water, which you converted using the molecular weight and density of water to the molar flow rate that you wanted, and that was you represented by W. And then you put that information also on that sheet. In other words, you updated all that information, right? And until you found out whatever was asked for and completed the question. So in summary, you can say that the first thing we did is write all values, write all units with units of all the variables at various locations of the various streams on that flow sheet. So you labeled all the known values with units, say mole per second, mole per hour, kg per hour, whatever, of all the stream variables, that is the arrows, at where they were entering or exiting the process unit or units. So that's the first thing that you did. Then second, you assign various symbols to it, such as, especially to the unknown, you assign unknown, symbols that it had Q or M dot or so much solution totally per minute flowed in, etc. Right? And you did the same thing for all the unknown components. Then ultimately you derived an equation for each unknown that was coming on this chart. And then you solve them by methods that you are quite good at. I have full faith on regarding that. So the only question is that we should always keep the number of these labeled unknowns very small, minimum, not add to the number of equations. And we must try to solve them in the right order, right? Then I left you with one little more difficult question: how to determine the number of linearly independent equations, right? So now again, the answer to this is not an easy job, not an easy job. The answer is not a simple one, but for our purposes, what are we doing right now? We don't have reactions. Suppose we have multiple reactions and all, the answer to this is a little tricky. But for the moment, the answer is not a problem for us, because we are doing non-react balances on a non-reactive system. So the rule for a non-reactive system is that we have as many linearly independent equations or items of information as we have components. In other words, in our benzene toluene system, non-reactive system, no chemical reactions, no consumption or disappearance or generation due to reaction. We had only two components, so we had equal to the number of components, so two linearly independent equations, that is, and the remaining were all redundant, right? So in our non-reactive case, the principle is very simple. We just look at the total number of components, and the number of equations that we need to, the linearly independent equations are only equal to the number of components. Okay, this rule of course doesn't apply in general, but for the moment we can use it. So now there's one more aspect which we would like to discuss, and I wanted to let us look at the slide so that now we go beyond this. What we have done. So now once you have all this labeled, everything, you have all the information on the flow sheet, what is one more thing that we need to next look at? So we were to look at you see let it load. Right. So those are the original ones. We don't need that graph. Yes, exactly. Right. Then you are trying to do balances. But now, normally, it's a very good idea to write down what is the basis on which you are doing the calculation. For a very simple problem, this was not a difficult. But it's good to write a basis, meaning, for instance, you can do the calculation on depending on the basis of the total number of moles of reactant per minute coming in. You can do it on the basis of limiting reactant, even if there is a reaction, or you can do it based on any one of the components. Say you can leave out air in that example and just do oxygen. So you can always say 100 moles per minute of oxygen flowing in. On the contrary, you can say 100 moles per minute of air flowing in. Alternatively, it can be based on the number of moles per minute of the exit product coming out, right? So it's always a good idea to specify, because otherwise it's impossible to correct to either. Then we get the answer. If you don't write the basis, and I've had this is only the second time I've taken this course, but the last time I had this huge problem. People never write the basis. Somebody does it based on 100 kg, somebody does it on 100 moles or moles per hour, whatever, and also reactant product, which reactant. When you have a reacting system, things become impossible to keep track of. You can do it based on limiting reactant, you can do it based on the total number of moles of the system, reacting system, to make out. So you must write down what is the basis, like 100 moles per minute of entering gas is a valid basis. So all your other streams, just as this slide says, all the other stream is calculated by balance equations that you know how to set up for those simple cases we did. All, as it says, are determined to be consistent with this basis. In other words, you determined whatever was to be found out, the symbols that you gave, the Q, the M dots, and etc. You found out based on the basis of the what you took as basis, right? So this is important. So the good thing is this is not a limitation for us, because you can always scale up a process. You may do the calculation per mole of something, but suppose a process unit will not be operating at 1 mole a minute. It will be having a much higher throughput, right? But then if the throughput is known to you, you can always scale it by that factor, right? And then all your answers will get scaled up by that number. On the contrary, if I were to only ask you some ratios, how many moles of exit flue gas per mole of total input, right? If it's a ratio, it won't matter, right? The basis will not matter at all, because it's a ratio, and later you can always find out for the actual rates, actual feed rates. So it all depends on what you are asked. But normally, if we are not asked ratios and we are asked actual numbers, it's good to start with a basis of 100 moles or moles per hour, 100 moles per hour, or 1 mole per hour, or what have you. And then later on, to at the end, scale it all up. That is what this slide is essentially telling us. Is it clear?
Yes, sir.
Right. So what we want to do today is an example on how we do this operation. It's a common sense thing, but nonetheless, if you do not scale up if the questions gives you an actual throughput of reactant or product, and if you don't scale it up, you will get a wrong answer, right? Normally, we want an answer which is to a relevant process, and that process will not be working on 100 grams per mole or 100 grams per second or 100 grams per hour or 100 mole per hour basis, right? But it's convenient to choose such a percentage type of basis. Okay, so that is essentially what this slide is telling us. Now, once a basis is chosen, you can do, as that slide said, you can do all the other calculations with respect to that. But one more thing, what we saw in the water example, where you got 10 by 9 moles per hour of water coming in, an actual feed rate was given to you, right? This is what the italicized slide is telling you. If a stream amount of flow rate is given in the statement of the problem, as it was in our previous classes example, it's good to choose that itself as the basis, right? Because then automatically it's relevant to that particular process, right? So if a stream amount or flow rate is given, you can use that as a basis. Suppose this is not given, then the second line of your italics says assume 100 moles per hour of water, etc. Right? Then, as it says, if the mass or mole fractions are known, find per 100 kg per hour what is the total mass or flow rate of that stream. You can label the oxygen and the nitrogen, etc. on that basis. Right? If the mole fractions are known, find the total number of moles or molar flow rate, and that you can put on your score sheet, which is the diagram that you have. So let us do an example, and this will give you a better feel. So first, of course, no actual flow rate is given, so it's almost like a problem of our previous class, right? So why don't you just simply look at that, first solve this, and then we can do a part B to it. Let us call the ratio. See, again, here a ratio, if you ask, as I say, if a ratio is asked, I don't need to worry about scaling up something. So anyway, let us calculate whatever is given here. First, again, you need to draw the diagram. It's again the similar type of problem, because there is only, see, as long as the rule is this, if there is only a single, what we find is if there is only a single unit, process unit, and we have many streams coming in this case, 2 streams coming in, 1 going out, that is not a very difficult job. But so our next problem after this, maybe another example we can do of this kind, little more detail on it, but we need to go to multiple units. So Thursday, definitely we want to do that. Anyway, so why don't you take a look at this aqueous solution of NaOH problem and first find all these ratios, which is like how many gram of H2O was there per gram of feed, or whatever he says, liters of H2, whatever volume or mass or whatever, and what is the grams of product solution per gram of feed. So that is based on the usual component balances and total balances. So why don't you first label the diagram and then we'll worry about how to solve it. Actually, the word worry is not a correct word in this context because these are very fairly simple examples. But gradually, things become tighter, and then we do have to worry about a lot of more things. We are still in the simpler part of the balance equations.
Sir, you've been muted.
1 minute, 1 minute. Yeah. Okay. Yeah. So first, there is only one unit. Please determine the number of streams going in and number of streams going out. The usual things. Let's first do that. It's a batch process or not a batch process. So would you call this a batch process or not? Sorry, it has got muted again. Um, so the rule was, if it is a continuous process, the balances are of a differential nature, that is per unit time. And if it is a batch process, then we can balance total mass, not rate. So in this case, this is indeed a batch type process, right? First draw the diagram of the input elements and label the output and label the knowns and label the unknowns by symbols. How many components are there in this question? Only 2. So how many streams should be there in your label? Both of them. Please draw that.
Sir, I didn't get one thing. Why is this a batch sort of process?
Because you are basically charging, say, a basis of 100 grams of NaOH plus water or feed solution. Nowhere are you flowing something at a constant flow rate. So it is not a steady state flow process for sure. However, it is input is equal to output would be the simple balance, because it is like a mixer. Just as you have in a lot of mixing units in a batch bioreactor, or like the cement mixer type of thing in which you see in construction sites. So I would say that this is a simple case of a batch system with a balance on a mixing unit. So you have to choose a basis, and I suggest 100 grams of the solution that is fed into this mixer. 100 grams or liter, assume the density to be 1. So on the basis of this feed solution, you can now work out the other unknowns. First, you have to identify the unknowns. I only told you that there are 2 flowing streams. Now find out what the output is and label all of the unknowns.
Sir?
Yeah.
So can't we take the mass of aqueous solution of NaOH as 1 kg and then proceed?
Yeah, 1 kg, 100 gram. Generally, I prefer a number of 100 rather than 1. Otherwise, every time fractions come. Something like a total feed solution of 100 kg or 100 grams, whatever, depending on the unit you want, would be a good basis.
Oh.
So, but we'll have to take it like kg per hour or grams per hour, right? Because it says diluting the stream of 20% solution, so it's supposed to be a stream.
Right. That's a wonderful point, I must admit. Very nice. Good question. So basically, what does that mean? Basically, what it means is that in principle, this can also be a continuous flow system. And if we were given the number of moles or amount of mass of the feed solution per unit time, that also this would be a valid problem, and that is probably what is happening in this process. Nonetheless, the mixing process itself can be evaluated based on a mass basis. That is the whole point. So if we were to add a B part to this, and I were to give you a molar flow rate or a mass flow rate, we can divide through the basis you have chosen by the given mass flow rate, and then you will have a certain mass of the feed solution per unit time, right? Mass upon mass
Yes,
per
sir.
time will give me units of time. It will give me units of mass per time. Mass upon mass per minute upon mass as an entire thing in the denominator will give me units of mass of the feed solution per unit time, which is what I want to do in the B part. So let us not jump the gun, but it's a very good point. Yes. The process indeed, as you have correctly identified, is a flow process. Yet, if I have a known amount of the stream in grams, I can find out all the unknowns in terms of, for the mixer, in terms of grams or liters or what have you. Because you see, what is asked is a ratio, right? Grams per water per gram feed solution, or liters of water per kg feed solution. So where is the time here? The time part just disappears, right? So when I have the ratio, I can definitely take a unit. They can take the basis as 100 grams of something or 100 kg of mixed feed. Am I clear?
So, yes, sir. So basically, my doubt was ki, like we can also consider this as a continuous process, right? Because
Yes, you can.
it says a stream.
Yes. Very nice. I agreed with you already. It's just that I wanted to we wanted to illustrate something, but you are absolutely right. It's a very good point you have made, I must say.
Okay, sir.
So this is VK. What does VK stand for?
So Vishantan Kumar.
Okay, so that's right. You are right. Nice. By the way, the total number of students in our class is now fairly large, right? It's more than 65, right?
Yes, sir, around 60, 65.
Yeah. So, but quorum means around half, but we are just not touching that, right? So, what do the other people do? Are they around, or I mean, they are at their respective homes, or what do I? Because there is nothing for attendance. So, in principle, so there are two components you have to worry about: the sodium hydroxide and the water. And the NaOH solution is being diluted, right, by a water solution. So please label all the knowns and the unknowns. And what is at the coming out at the exit?
8% solution.
Correct. Do you know the amount or flow rate of the output solution? No.
No, sir.
That's a variable. What is the other variable?
Inflow rate of the 20% solution and the water stream.
But one of them you are going to take 100 something, whatever.
Yeah.
Oh, you cannot keep both of them unknown. You are going to do the calculation based on that basis, right?
Yes, sir.
So you cannot say both are unknown. For 100
Since it asks the ratio in terms of feed solution, we can just take the feed solution as a known quantity, fixed quantity.
Why not? You can do that. Take 100 kg or for feed solution, or 100 grams feed solution, or I don't know, maybe volume if it's asked in volume. I don't know. It's okay if the density is 1. It's interchangeable. The dilute solution, so. So if initially the composition is given 0.2 grams, it's by weight, no? So 0.2 grams of NaOH per gram of feed solution. So the remaining is water, right? So please label that. And that is being mixed by it is being diluted, is the word I was looking for, by a water solution. So that flow rate you do not know, or that how many grams you are adding to the 100 grams of the feed, that you do not know. So that is definitely an unknown. So label it. So you will have two unknowns. One is the input unknown, and the output unknown, of course, you do not know, though you know the composition again. So it's diluted, no, from 20% to 8%. So the water stream is unknown, and then final rate or amount of the stream is not known. So based on the previous thing, because it's unreactive, we have only two components. So we have two independent equations. So now you can balance and write those two equations. So flow rate is, let us see what it is. Exactly. So he took 100 kg. I was talking grams, doesn't matter. 0.2, yeah. So that was the fraction, because you told me it's 20% by mass. So he has converted that to per kg. That's the input. Then from the bottom you have so many. Again, he has put in liters. It could be kg. Okay, kg H2O. That is the dilution. That is due to the incoming stream of water. And then you have the 8% composition coming out, and M1, M2, according to him, are the unknowns. So we can do an overall balance, and we can do a sodium hydroxide balance, and we can get those two unknowns. So please do them. You know how much total feed was there. Just now you told me 100 kg you are taking, so you know its composition. Initially, you know the composition finally, so M2 you will be able to find directly by the sodium hydroxide balance. Okay, let us break that also. How much sodium hydroxide is coming in?
20 kg.
Exactly, 20 kg, 0.2 into 100. How much is going out?
M2 into 0.08.
M2 into 0.08. It's a simple equation to calculate M2. So find what M2 is, 250 kg. Now do an overall balance, since total mass has to be conserved. So find the amount of water from the bottom stream, or M1, that you use. How much is that? Because your basis was 100 kg, so it has to sum up to M1 plus M2. Or rather, 100 plus M1 must equal M2. So from those, you know Q2 M or M2, and so you can find out M1. How much does it work out to be? 150 kg. Now find those ratios that he asked for. How many kg water per kg feed solution? So you know you took 100 kg feed solution. How much of water did you put? That was Q1. So 150 upon 100. So it's 1.5 kg water per kg feed solution. Similarly, find the other ratio. So you also know the product now.
It will be 3/5 liter per kg ratio.
Right. So you will get 1.5, 150 kg per 100 kg, so 1.5 kg of water per kg feed solution. And also, you know, the output M2 was 250, so 250 divided by 100 was the grams of product by gram feed solution. Very nice. Now, suppose a scale factor was actually given to you. In other words, what is the true flow rate? Like you said, it is a flow problem. Suppose the true flow rate of the product stream or some other stream was given to you. Then suppose, let's take a number. Okay, in a B part, suppose the product stream is given to you you have to produce a flow rate of 2300 kg per minute. That is of the output solution with the same 8% by mass NaOH. So the flow rate of the product is given to you as 2300 kg per minute. Now find the feed solution flow rate and find the dilution water flow rate. How will you do that? So this, all you have done is you had a basis. So I said you can always find the scale factor by division. You took the basis, you have given the actual flow rate of the product in this case, and then based on the how much product you actually had and how much product per minute you are producing, you will have a scale factor. How much was the total product that you had for 100 grams or 100 kg of feed solution, which is M2? How much did you get? 250.
250.
Right. Now, the actual flow rate of the product stream is 2300 kg per minute. So what is the scale factor? Definitely 2300 divided by 250.
Yeah.
One is in kg product per minute upon the kg of product. So that will give you the kg per minute per kg of the product. So approximate whatever 2000, that's approximately 9. That's your scale factor. And everything you will have to multiply from your original basis, you will have this number. And that will give you the correct units of kg feed solution per minute or kg feed solution, kg of water per minute that you are flowing of the dilution water. If you multiply what you answer that you got by this scale factor, then the time scale will also come and the per minute will also come. And so in that sense, it just become a flow process as VK told us. So the scale factor is approximately 9, which is the ratio of 2300 by 250, because one was the grams of the product, the other was the grams of product per minute. So everything in your, of course, I mean, you could have started with 2300 itself. But this is a simple question. It was not difficult. But my point is there can be situations where you have multiple products and then it becomes very difficult to, so don't want to start with the actual number. I don't know, you can do whatever, it doesn't matter, but then please write it. You can say I start with 2300 pounds product per minute or whatever is given to you. I just said that you can always convert one basis to the other by scaling it up. Generally, it's a scale up, right? So now find out the feed solution flow rate. So that would be, you took the basis of 100, so multiply by 9 and find the dilution water flow rate, whatever was the flow rate for water, I mean basis, how much grams of water you found, kg of water. This was 150, multiply that by 9. That is your actual answer to the. That is the actual feed rate of the 20% solution and the actual feed rate of the diluting water in order to produce the output of per minute of 2300 kg. Are you all okay?
Yes, sir.
Right. So essentially, choose the whole thing is choose a basis. And on the basis of that, you can always scale up and find out. If you are asked only to find a ratio, then you don't even need to worry about the actual number. The actual product flow rate, in this case, to the 2300. But many times you may have to actually, nobody wants just a ratio. Sometimes you want the actual numbers, so you need to scale it up, which is the division of the given number divided by the basis that you chose. You can do whatever you want, but please write that basis on which you did the original calculation. Okay. Now, I think slowly we are coming to a stage where we have to add some more complexity to all of this. And maybe tomorrow, no, day after tomorrow, or we can try one of the continuous questions if you want, and then we want to go to multiple units. Then things become somewhat more challenging and more interesting, I would say. This all we have to start with these simple things and go on to more and more, and still we are only on non-reactive systems. So okay, so we will continue from here, and let us see what we can do Wednesday, and when we can start the multiple unit problem on Wednesday, or perhaps Thursday morning, Thursday 12 o'clock. Okay, so see you Wednesday.